Welcome to another problem session. So this is actually in the standard problem in rocket motion, and I'm going to cover all of it. Okay. So the question is find the equation of motion for the rocket, which is this part, um, part in the blue, and once you find the equation of motion for the situation given at time t and time t plus delta t, then solve if there are no external forces, like like if the rocket is flying through some debris, there will be external forces on it. If the rocket is in gravity, is going to be some external forces on it. So solve for first there's no external force, and then solve for just gravity. And there's going to be a lot of time here, and there will be fourth is like when rocket is flying through maybe a star dust cloud, just going through the dust, and the dust particles hit as the rocket is going, and so there's going to be impulse from the dust particles, and so there will be external force like that. So I'm going to be later, not this time, but later, rocket through stardust. There I have to say of density some rho, and maybe stardust is at rest, but when the rocket is going through it, it's going to encounter the dust particles coming at it, and that's how you're going to get the impulse. Okay, so this is going to be later. So let's do these three today, the standard, and I think you're going to learn a lot. All right, so so here's the situation. So rocket has this total mass of the rocket is m and delta m, and they're going at time t and going at speed v, and the center of mass is over here. So all this this v is with respect to some frame that's fixed. So this is some inertial frame. So this v is with respect to this frame, okay? In this frame. So there's someone looking from here, it sees that's the velocity, and that's that way. Just a vector, it could be any arbitrary direction. Okay, whenever you read the problem, when somebody says velocity, you really must ask the question, what is the frame that with respect to this number is going to be given, okay? Because if you don't ask that, then you're not specifying the problem fully. And this is one of the problems with rocket motion, when you encounter in textbooks. So that's the velocity with respect to this frame. Now when the rocket is going to moving, it's going to eject out the fuel, and I'll give you u with respect to the rocket itself. So now this u is with respect to not this, but u, this thing is going back from the rocket, is when I'm in the rocket, what I will see is this u. But when I'm here, I see this guy going with a change velocity, used to be v, and now it says this much velocity. And I'll see that to be a different velocity, right? Velocity of this guy will be different. So got first write down the velocity of each one of those guys with respect to the same frame, okay? So let's write that down. So the velocity of delta m, now this with respect to O, this guy. So this, what will this be? This will be the velocity of this guy with respect to O, which is this guy, plus the velocity of this guy with respect to that. So velocity of Cm of this rocket after it ejected. Okay, I'm gonna call this r prime. Okay, with respect to O, so this is going to be one quantity plus velocity of delta m with respect to the cm r prime. So these two things. This one is this guy. This is the v plus delta v. And this is, instead of minus, I'm writing a vector notation, so I'm just going to add and make it u. If I put a coordinate system, it might be minus, okay? But right now, we're using only vector notation. So we know this whole thing with respect to this, and we also know this whole thing, everything in there with respect to the same frame, and with respect to this inertial frame. So in inertial frame, the law is dp dt is f. That's the law. Okay, so we need to figure out left side and the right side, and this f is all the external forces. All right. Yeah. Okay, so how do I figure out this guy? So we already know what is time t, what is time t less. So we have to just, so what is the p at time t plus delta t? That just turns out to be also the masses. I forgot to mention mass of this part we're going to call m, and mass for this part we're going to call delta m. So that's m, and the one that's going to get ejected is delta m. Okay, so this is a standard way of accounting for the masses. Okay, so you have a m times v plus delta v. So plus delta m times v plus delta v plus u. Cool. So far good, right? And so p at t is just both of them going at the same velocity. Over there, both of them are going the same velocity now, right? So m plus delta m, that's both of them are going with velocity v. Now we need to subtract this and divide by delta t, take a limit, right? So pt plus delta t minus p of t over delta t, and take a limit, delta t goes to 0. This is the process I have to do to get dp dt, and this is all vector. Okay, so this, you will see why I need to do it this way. So this is this part and this part cancels out. So this part will cancel this part out with that, and delta m times v, this part will cancel this part. So we are left with m delta v plus delta m delta v plus delta m u over delta t. Okay, so the first one, let's separate the terms out. M delta v over delta t, delta m delta v over delta t plus limit delta t goes to 0 of delta m over delta t u. So here is the thing that we don't know how this is going to behave, so I'm going to do delta t times delta t. So over here, this is the rate at which the mass of the rocket is changing, and this is the velocity at which the rocket is changing, and this is the mass rate, and this is the acceleration, same ways, right? So we got m dv dt. This is the velocity of the rocket itself is changing because that was the velocity. V was the velocity of the rocket. And this one is pretty interesting. This term becomes delta t goes to 0. Delta t times dm dt is going to become, and the other is going to be dv dt. So these are all finite numbers, rate at which things are changing, finite. This is going to, but this is going to go to 0. So this whole thing, because of this, will go to 0. So last term is dm over dt u. Now, it used to be over here m plus delta m. Over here, there's too much of a change. Over here, the rocket just became m, and then you had a delta m, it lost delta m. But you can see if I define mass, let's call it mass of the rocket, everything like mu. So this is like a rocket's, let's call it mu. Then this is going to be smaller. Mu t will be m, and this will be m plus delta m. So you can see that amount of rocket's mass actually went down. So if the delta m is a positive number, then mu is a delta m over delta t is positive, then delta mu over delta t will be negative number. So its mass is decreasing. So we can write everything in terms of mu, and normally people will say, okay, write everything in terms of mu, so you don't get confused. So mu for the rocket mass, okay, rocket's mass. Then this is just a mu of t dv dt, and this is 0, and this is going to be minus d mu dt u. I think it's just, it is that. So if this is positive, then this is negative. So but they're equal to each other in magnitude. So the relationship dm dt is same as minus d mu dt. So there are lots of m's here and little m's here. That's pretty confusing in the treatment. And at this point, I say, oh, let's invent another symbol, so they'll keep track of what's the mass of the rocket is at any time. And delta m is going to be, this delta m is infinitesimal. So it can always be made as 0, as small as you like for your argument. So delta m has not that big a meaning. What is the meaning is dm over dt, okay? Because delta m will go to 0 with delta t go to 0. But so you can see delta m goes to 0 as delta t goes to 0. But delta m over delta t does not go to 0, does not go to 0. It goes to dm over dt, the rate at which the mass is dropping as delta t goes to 0. Okay? So if you make the arguments, the rocket equation using m and delta m, it's very confusing. You got to be very sure about what happens when delta t goes to 0. That is where you're going to get clarity in your thinking. Okay, so we got this thing is equal to this whole thing. And at this point, if I'm totally okay with it, I can go back and call this guy M and dm dt u. So you can go back and rewrite with the original symbol. All right, so we've got this is equal to dp dt. On the right side is f, so the f external. So the equation of motion of a rocket, no matter how complicated a rocket is, whether it's Elon Musk's rocket, SpaceX rocket, whatever, it doesn't matter, Falcon 9, it's all of them are, equation of motion is very simple, okay? It's just mt dv dt minus dm dt u, and this u is with respect, right? It is a constant, right? So u is a constant rate at which you're burning, assuming it's burning at a constant rate, and it's going back at a constant velocity. So it's kind of some constant vector. So u is normally, I'm going to take as a constant velocity vector, and it's pointed towards the back of the rocket. If you want rocket to go forward, if you want rocket to turn, this u will be pointed some other direction. Okay, but the direction is with respect to the center of mass of the rocket. Okay, direction is with respect to center of mass of the rocket. All right. So this is the equation of motion. Now I need to solve this. So this solves one. For number two, I need to say this is 0. Okay. Then starting from v equal to 0, so I'm going to say v at t equal to 0 is 0, just for simplicity. What will be v at t? Just when the rocket, all this time you're burning this fuel, okay, at constant rate. So we need to solve, this means to solve this, therefore solve this equation with the 0 on the right side. Okay, so case is f external equal to 0. This is outer space, no hitting any debris. It's just vacuum. It's not coasting, it's trying to accelerate, okay, by burning fuel. So that's the part we're looking at. So we have a m dv dt minus dm dt u equal to 0. All right. Clearly you can just multiply by dt and this becomes m dv equals to dm or u dm. Okay, so bring m on the other side, but this is the one we integrate the variables. So you have a dv equals u dm over m. And because from time 0, we can do time 0, although time is not here, we're going to do time 0, so time t. So we're going to do that. So time 0, this side is we are doing actually vector integration, but you can just do it component wise if you like. And this will be velocity at t, and m at a 0, and then m at t. This what usually you say mt, this m0, and this like m at t. Is sometimes people write like that. This is easier notation. And so we integrate from v at 0 at v at t, and because of this m, we're going to integrate from m0 corresponding to that, corresponding to mt corresponding to that. And this is constant, so we're going to take a constant vector, so this will come outside. So I'm going to get v at t minus v at 0 equals to u integrate dm over m, m0 to mt. So now this integral is log. So u is going to be log of m, m0, mt. So u log m, t log m0, which is division of the log, u log mt over m0. So we've solved it, and in case of that, it just v at t is just u log mt over m0. And you can see that this is bigger than that. So let's write down minus u log m0 over mt. So this is now positive. So this velocity is in the opposite direction to the u, which we know. This is the velocity of rocket. And this u is of the ejected fuel. But u vector itself is with respect to the rocket. So that if u is pointed back this way, then this guy is pointed that way. So they're opposite direction. So delta m, u is pointed that way, then this guy is pointed that way. That's what he's saying. So u is a vector. That's actually very, I know a lot of students have this confusion. Where's the u? And they're going to mess up the sign. And because of that, they mess up the sign. If you really don't want to keep just a component, just keep the component, just take this as an x-axis. Then this is going to be vx at t minus ux log m0 over mt. And if u is pointed that way, then of course so ux will be minus u. U is being the magnitude, okay? So this is going to be plus u log m0 over mt. U is greater than 0, is magnitude. Magnitude of the u vector, that's magnitude of u vector, which is like u is u vector, this. Good. I hope this clarifies a lot of things that you may have misunderstood before. And if you haven't misunderstood before, that's great, okay? You are doing very well. So let's do the other one. So here is I'm going to do rocket shoot up. So the gravity is pointed down. So G is pointed down. And this time, let's do this, like, let's call this x-axis. So the V will be Vx, V equals to Vx I hat, and the U is pointed down, then U will be minus U I hat, okay? And the equation that we need to solve is this in the x component. So okay, so m dvx dt, this minus u vector minus u sub x is minus minus becomes a plus u dm dt, and the other side is going to be this is going to be negative minus mg big M. Okay, same. These m's are all same. All right, so we can just divide everything by m, divide everything by m, and multiply everything by dt, multiply by dt, multiply by dt. So what we're going to get is dvx from here is going to be u dm over m, and this is going to be minus g dt. Okay, let's integrate some v0 to v, and so this integrate m0 to m at time t, v0 v sub t, let's keep it 0 to t. So all these integrations correspond to the appropriate variables we are integrating, right? So this is like from initial to some final. So each one of them has got the appropriate symbols for initial and final. So I'm going to get vt minus v0 from here. I'm going to get u log mt over m0, and you're going to get a minus g t, zeros. Okay, so you can see I can put this on the other side. So vt equal to v0 minus u log mt over m0 minus gt. Okay, so look at what's going on here. This one is bigger than that, so I need to invert the log so that it becomes positive. So this is going to be v0 plus u log m0 over mt. So now this is positive and this is positive, so this is vt is increasing, right? Yes, but there is a cost to be paid. gt is, you have to work against the gravity. So you can see if I multiply by momentum, then it's actually, look at this, m. So this is the thrust part, and this is the cost of gravity. So you have to pay this much to overcome the gravity, and so you can just bring this on the left side just to say, so to have this momentum change, you have to provide this much thrust and more. This is actually there will be fuel burnt to, some of the fuel burnt will go towards overcoming the gravity, so if this wasn't there, it's going to have much more momentum change, right? But because it's there, you got a little bit less momentum change, because you have to, some of the fuel was burnt for overcoming the working against the gravity. So this is the negative impulse of gravity, which is you have to work for, right? Or work against to overcome it. Okay, so this is what thrust, and you can look up some really figures, gigantic figures for these m's and the v's and the thrust. Uh, so I'm just doing it at this is m is just a mass I put in just to give you a sense of the force involved, and you can just say I'm in doing that m sub t got multiply the same. So this is happening at time t. All right. Okay, I will leave it here. This is later on, if you have not just this, but you say you're going through interstellar dust, you're going to have another way the fuel have to be burned to overcome the impulse from the hitting particles opposite to you. And we will handle that when we talk about how the impulse from the hitting particles actually can be accounted for. I think I'm going to stop here. It's a pretty instructive video. I hope a lot of things got clarified or reinforced. So I will see you in another video. But meanwhile, tell your friends. If you haven't really subscribed to this, you subscribe. Sometimes it helps make more people notice and find these videos online. If you hit the like button, or if you want to interact with me personally, you want to send me some feedback, yeah, I appreciate that. So you can do comments. Okay, so enough for those advertisements. I'll see you in the next video. Bye.